And it's TEK 9. Hey gang, it's time to keep working on our final exam review, but just for you, new nails. Look at that, won't that be fun? Okay, so TEK 9. We're going to do a lot of domain and range with exponential functions. We're going to write domain and range with exponential inequalities, lots of exponential stuff. And this is all TEK 9, A, B, C, D, and E. I can use my calculator to write exponential functions that represent data. Okay, lots of exponents. Exponents was one of our most difficult topics that we did. We did it the whole month of January. We did it in February as well with functions. And then we ended with polynomials in March. But anyway, let's just start off here. 9C. Suppose you deposit $5,000 in a savings account that pays 5.8% interest compounded annually. Write an equation that best represents this exponential function in the form y equals ab to the x power and models the amount of money in your savings account for each year, for any year. So we've got y equals, oh, my pen's done. Let's change pens. There we go. Y equals ab to the x power. With exponentials, remember a is the starting amount. How much do I start with? In this situation, I've got a savings account, and so my a value is going to be $5,000. And then remember, when you're working with exponential, and you're talking about growing or decaying, which is usually what we're looking at. You're either growing really fast like this, or you start tall and you decay down low. Exponents looks like that. We talk about having 100% of something. We're always talking about these percents, so 5.8%. Here's the way I look at it. Whenever you're working with exponents and they're talking about like growing interest compounded annually, so it's getting bigger, right? I'm investing $5,000 and I'm going to get more. So I invest, and this is representing 100%. I'm investing all of that. I'm not investing half of it or a small portion of it. I've got 100%. No matter what you do, whether you're growing or decaying, you always start with 100%. I'm talking about this pen. I got 100% of that pen right there. That's mine. So I say that because whenever you're working with percents, always assume that you start with 100%. You can't get less than that. We'll start with 100%, and I'm either going to get more of it or I'm going to decay and have less of it. In this situation, I'm getting interest at 5.8%. So I'm going to say plus 5.8. Whatever I'm adding on or subtracting, I'm just going to put it in there right like that. So 100 plus 5.8 will give me 105.8%. Here's the trick. You can't put percents into this equation. So what I do is I have to fix it so that it's no longer a percent. So I move the decimal point over 2, and it becomes 1.058 as a decimal. Okay, here we go. So y equals a, which is 5,000, b, which is the rate, which is 1.058 to the x power. X is the exponent, and that gives us exponential functions. All right, so yeah, that works. Y models, I got to get my glasses, I cannot see this. Amount in your savings account for any year X. Yep, so we're good. So here we go. So if I wanted to know in 10 years how much would I have in my account, I could plug a 10 in right here for X, and I could figure that out. Okay, on to the next one. A student used f of x equals 125,000 times 1.02 to the x power to see how, or to show the balance in a savings account will increase over time. Label the following. What is the A value? Well, we just talked about A over here. A is the starting amount. So we've got 125,000. And would you say if I'm talking about money, I should probably put a little dollar sign right there? Yeah, I'm thinking that might be pretty good. And what does the A represent in this particular situation? Well, I'm talking about a savings account, and A is always the starting amount, just like it was over here. So it's how much the student invested initially. It's the initial value. Initial value invested, or initial money invested. Initial value invested. 125,000. And then I'm going to put over here starting amount. That starting amount is the key. That's the one that we're always looking for when we're talking about that one. Okay, 16. The function f of t equals 300 1/4 t represents the number of moose in Yellowstone Park after t years. If this function is graphed on a coordinate grid, what would be the meaning of the y-intercept? Well, if I were to graph this, and I'll show y'all, you're not going to be able to see it. And I wonder why. Can anybody think of, Miss Dean, why can't you see that? 300 parentheses. Okay, I'm going to be real lazy here. 1/4 is the same thing as 0.25 as a decimal. I got the hiccups. To the x power. I'm going to hit graph. And I'm not going to be able to see it. Because, and I've asked this on a test before in my class, 300 is way too high. So 300 is way, way, way up here. So I can see it as it comes down. I can't see that 300. Because what is 300? 300 is where it crosses the y-axis. What does that represent? Let's actually do this. Let's come over here. Let's draw a graph. This up here would be 300, and our graph comes down like this. So what does that 300 represent? Hopefully you're saying it to yourself, Miss Dean. Just give me the answer. It's the initial amount of moose in Yellowstone Park. Now, I know for a fact there's more than 300 moose up there. So, but what would the meaning of the y-intercept be? The initial, the starting, I'll say starting because we always use that word starting. The starting amount of moose. Moose, meese, mice, right? No, I know. I know, you know, it's moose. Okay, number 17. The table shows the growth in a school district's after 5 decades. Now, I'm going to wait and tell you that part in a minute. Okay, decade 0. So this is our start. Then we have decade 1, 2, 3, 4, 5. Population Y is 12,321. Then it goes up, up. So it's definitely increasing. Predict the student population after 80 years. Okay, so let me move that over. Since they're wanting me to do predictions and correlation coefficient and describe the correlation, I can tell you just by looking, is it going to be a positive or a negative correlation? Yeah, it's definitely going to be a positive. It's trending up, so we're going to call that a positive. But I'm going to go to my calculator. I'm going to go to Stat. I'm going to go to Edit. Oh my gosh, what's really funny is I had an energy drink. I think that's why I'm talking so fast. I'm like, blah, blah, blah. Miss Dean, going crazy. Okay, here we go. I'm going to put in 0, 1, 2, 3, 4, 5. Now I'm going to go over here, put my Y's in. 1, 2, 3, 2, 1. 1, 3, 2, 5, 8. 1, 5, 6, 4, 8. 1, 6, 2, 1, 4. 1, 8, 0, 2, 1. And 2, 0, 2, 5, 9. Okay, so I'm working with exponents, right? Predict the student population. What is the correlation coefficient? Describe the correlation. Oh, you know what? 9E. The table shows the growth. Okay, when you're talking about growth, usually you are talking about exponential. This one, I would have to tell you, and I don't in this problem. I should have told you that it shows the exponential growth. TEK 9 is exponents. If I just ask for a correlation coefficient, I might be thinking linear on this one. I'm not sure I can even do that on this one, but we'll try, because that's a linear thing, correlation coefficient. So here's what we're going to do. Actually, you know what? No, we're going to change this to linear, because this is a linear question. We're going to say linear growth. And I bet on your test I already added that in. So anyway, because I'll do corrections on it before I print it. All right, so we're going to do Stat. We're going to do Calculate. We're going to do number 4. And we're going to enter all the way through. And there it is. Now, real quick, if your calculator does not show the R, remember, like if you just see Y, A, and B, and you're like, well, mine doesn't look like that. Hit Mode, and you want to go down to Stat Diagnostic, and you want to turn yours on. Okay, stat diagnostic, turn it on. And then when you go do your stat regression, it will work then. Okay, so go down to mode, stat diagnostic, turn it on. All right, so here it is. So I'm going to come over here, and I'm going to write, oh, that's a big mess, isn't it? So predict 80 years. So I'm going to have to do this again. Stat, calculate, number 4. What should I do right here to make my life a little bit easier? Store. I'm going to store it. So we're going to hit alpha, y equals, and we're going to scroll over until we see that y1. There it is, y1. I want to store it right there because that y1 is this one. Enter, enter. There it is again. Let's go ahead and do our correlation coefficient. Correlation coefficient is R. It is 0.9. Remember, we go out 4, 9, 8, 9, 2. That would be a strong positive or negative. It is a positive. A strong positive correlation. Okay, I'm going to go to y equals. Now, okay, and it stored all that for me. I'm going to go to second table. Now the question is, do I need to scroll all the way down to 80 years? Do I need to do second table set and put 80 right there so that I can see what year 80 would be? Wonder which one. 136,732? Wow, that's pretty big. I'm going to tell you guys, no, that's not what we do. I'm going to go back here and change this back to 1. Second table set is what I was doing there. I'm going to go back here. And now I want you to notice something. Let's go back up to 0. 12057. That's almost that, right? 13258. That's pretty close. Because remember, with regressions, they don't match exactly. They're just in the ballpark. They're just close. These are all close. So I'm going to point out now what I don't know you caught before. The word decades. How many years are in a decade? Oh, that's right. There's 10. So this is times 0. This is 10 years later. This is 20 years later. 30 years later. 40, 50. So where do I need to go on here? Yeah, I just need to go to 8. So the prediction in 80 years, which is 8 decades, is 24,525 students. Okay. All right. A little bit tricky. Hopefully I did go back and put linear there. If I did not, just change it to linear. I need to go back and look at that TEK. I'm not sure why that one's here. Okay. The graph of the exponential function shown on the grid below, based on the graph, which statement about the function is true? So I'm looking here. I'm just going to kind of look at it. I can see that it's growing. I can see the y-intercept right here at 1, which would also be considered my starting amount. And it goes forever this way. I can see that. So let's look. The range. Okay, so it says the range. So I'm going to put the y. So that means I'm looking here. Is the set of all real numbers less than 1? All right, so here's 1. The graph, if I look at that, it goes up here for forever. Yeah, that looks good. But what about this little bit of the graph down here? It actually goes all the way down to what? Yeah, it goes all the way down here to 0. And then this right here, the line that it gets really, really close to but never touches is the asymptote. That line right there is y equals 0. It gets really, really close to that, but it actually doesn't touch it. Even though it looks like it does, it never does. Okay, so the domain. The domain is a set of all real numbers. Yeah, that would be right if they stopped there, but then they say greater than 3. No, because this goes forever and ever in both directions. So anything with domain, it's probably going to be wrong. The domain is a set of all real numbers less than 3. No. Okay, so it's these range, but I'm not thinking it's this one. The range is the set of all real numbers greater than 0. Yeah, that looks good because it's going up. I'm going to highlight it. If I look right here at the y-axis for the range, it starts here and it goes up. It's not down here. It just starts right here and goes up. And it doesn't actually equal 0. It's just, it gets really, really close to 0. All right, so we got C. All right, guys, so that includes TEK 9.